So it's a real pleasure to introduce Jim Saiers, who really doesn't need much of an introduction, but I thought I'd read out some of his past accomplishments in case not everyone in the room is familiar with them.
This shouldn't take long.
So Jim is the Clifton R. Musser Professor of Hydrology. He studies water quality and supply. He runs experiments, he collects observations, he develops models to understand how humans and human activities affect the chemical composition of drinking water. Drinking water as well as freshwater flows within aquifers, wetlands, and river basins. His most recent research projects address water quality impacts of fossil fuel development, carbon and nutrient transport through watersheds, and climate effects on water resources in Africa. Jim is a past editor of Geophysical Research Letters and associate editor of Water Resources Research. He has chaired and served on a number of NRC committees, including the one on Everglades restoration. He's also served on EPA's advisory board for the study of the effects of hydraulic fracking on drinking water resources. He's been funded by a variety of federal agencies, including NSF, EPA, the Department of Energy, the USGS, and a number of private corporations. Jim has a bachelor's degree in geology, and he went on to do a PhD in environmental sciences at the University of Virginia. Right after his PhD, he had a short stint at the Florida International University, and then we hired him away in 1999, and he's been here ever since. Many of us in this room have to applaud and thank Jim for his many years of service as the Associate Dean of Academic Affairs, and then his brief stint, but very important tenure as the Interim Dean. So please join me in welcoming Jim Saiers.
I see a few familiar faces in here that have come to my talks on shale gas development before. I'm going to start off, some of the front matter will look familiar to you, but I have some new results to present that no one's seen before. I'd like to begin by recognizing my co-authors. Erica Barth, who's a PhD student here. She's a full-on partner on this research project. Erica has led the field work and a lot of the laboratory work. Jae-Yoon Song is a relatively recent graduate of our Masters of Forestry program. We persuaded her to stay on to work as a technician for a couple of years. Deanna Cox graduated from FES in 2017. Deanna helped a lot with the laboratory work, and she probably has the most extraordinary set of organizational skills that I've ever encountered. And Mario Soriano's a relative newcomer. Some of what I'm going to present today has been informed by conversations with him on groundwater flow. So I suspect that most of you have heard about hydraulic fracturing. It's appeared quite a bit in the news. Industry doesn't like to put the K in it for some reason, but the rest of us do. So hydraulic fracturing involves injecting large amounts of fluid into an oil or gas bearing reservoir to crack it open, to increase its permeability and allow the gas or oil to flow out. Hydraulic fracturing in coordination with horizontal drilling has facilitated the economic recovery of oil and gas from a variety of shale basins and low permeability basins throughout North America. And this has led to a real boom in domestic production. So hydraulic fracturing, without a doubt, has contributed to making oil and gas cheap, right? This has lowered prices at the pump. A lot of this comes from crude oil coming out of the Bakken Shale in the Permian Basin in Texas. Hydraulic fracturing is contributing to lowering greenhouse gas emissions, and that's done as relatively clean burning natural gas has displaced coal for electricity generation. And it's increased the competitiveness of U.S. manufacturers that rely on hydrocarbons to produce various goods ranging from steel to fertilizers to a variety of petrochemicals. So these are benefits, okay, undeniable benefits, but still no one likes fracking, all right? So you wonder, well, how can that be in light of all these benefits? Well, part of it probably stems from the recognition that in the end, natural gas and oil are fossil fuels, all right? So if natural gas displaces coal, by burning it, you're still emitting fossil fuels and contributing to global warming, all right? But probably the biggest concerns stem from its widely publicized potential effects on groundwater quality. And the effects of hydraulic fracturing were sort of brought to center stage through a number of videos that were widely disseminated showing people from Dimock, Pennsylvania, and a few other places igniting their tap water on fire. And they were able to do this because that tap water contained methane, natural gas, all right, presumably from fracturing. All right, still others cases, people showing up at public meetings, showing obviously contaminated drinking water here, and asserting that this was from the process of hydraulic fracturing. Still other people saying, well, the consumption of this water has made my pets sick, my livestock sick, and people in my family sick. So EPA responded to this, okay, and they commissioned a 3-year-long study, and it was to look at the life cycle effects of hydraulic fracturing on drinking water, okay. Following this 3-year study, they issued a draft report, and the line that was picked up is the following. We did not find evidence that fracking has led to widespread systemic impacts on drinking water resources in the United States. All right, industry cheered, all right, environmental organizations bristled. So this draft report was reviewed by an independent scientific advisory board, and they altered the conclusion. The altered conclusion was hydraulic fracturing water cycle activities can impact drinking water resources under some circumstances. Impacts can range in frequency and severity. Industry bristled. Environmental groups applauded. Okay, so what's going on here? Between the draft report and the final report, there was no new data, all right? But the conclusions seem to change. So the question's who's right, all right? Is it homeowners alleging that fracking has contaminated their drinking water with toxic chemicals from fracking and methane? Or is it fracking proponents that claim that contamination was there before, we had nothing to do with it, all right? It's not our problem. So we were interested in trying to inform this debate with what we thought was some sorely needed observations and data. And about 2.5 years ago, we began a study looking at changes in water quality, groundwater and stream water quality in northeastern Pennsylvania, in a portion of the Susquehanna County that overlies the Marcellus Shale. Susquehanna County is sort of a sweet spot for natural gas development. And so this study is unique, and it's a prospective one. Okay, we were able to look at water quality responses through the life cycle of shale gas development. Okay, the life cycle in shale gas development involves several stages. One of them is hydraulic fracturing, all right, but it includes others as well. And since I'm going to talk about those stages and refer back to them in context of our water quality data, I thought I'd spend a little time discussing them here. So the stages that we're going to focus on are preparation of the site for drilling, the process of gas well drilling and casing, hydraulic fracturing, and then gas well production. Okay, so site preparation begins after the leases have been signed. Okay, the leases in Pennsylvania are typically between a natural gas production company and a private landowner. All right, the lease compensates the landowners for the gas produced and allows the production company to stay on that land. And so after the lease has been signed, permits have been obtained, the land is prepared. And what this involves is sort of preparing the land, a football field size area, to accommodate the gas well, and also lots of equipment required to drill and frack the wells. And so typically these well pads are on hilltops, gets them far away from wetlands and rivers, which is a requirement. And to prepare this land in Pennsylvania where we're working, forested land typically, involves a certain amount of clear cutting and also recontouring the landscape to flatten it out. Also, you've got to support operations there, and these well paths typically are in rural areas far from established roads, so there's a lot of road construction that goes along with this. So after the well pad is prepared, the next step is drilling, okay? And Marcellus gas wells are horizontal wells. They consist of a vertical section, okay? And this vertical section reaches down into the Marcellus Shale. That vertical section's about a mile long, okay? And then they bring in a drill rig that can drill horizontally. And this drills a borehole that parallels the gas-producing layer, in this case, the Marcellus Shale. That horizontal, that lateral, can be quite long. Typically, in Pennsylvania now, they're exceeding a mile, okay? So, gas well is more than just a hole in the ground, but it consists of, once the borehole is drilled, concentric pipes or casing, steel casing, that are each surrounded by cement. All right, so in this case, the interior pipe is a production casing. That's surrounded by another bigger pipe, the intermediate casing, which in turn is surrounded by the surface casing and the conductor casing at the top. Okay, the purpose of this steel casing or this pipe is to maintain the integrity of the borehole and allow the gas to be delivered to the surface. But equally important from a water quality point of view, is supposed to isolate overlying aquifers, okay, from the shale gas well, all right, thereby hopefully protecting the aquifer. Okay, so drilling is usually accomplished in 2 steps. Typically takes about a week to drill a shale gas well now. They've gotten faster and faster. And it starts off with sort of a small drill rig, and this is an example of one of those. And this drill rig is on site to drill the top hole, the vertical section of the well, down to about a mile, all right? So it's getting close to the Marcellus, all right? And this is an air rotary rig, and it uses compressed air as the drilling fluid. That cools the drill bit and brings the cuttings back to the surface. All right, here's that same drill rig at a slightly different stage. Now what it's doing is it's hoisting up surface casing. This casing, that's the steel pipes, about 14 inches in diameter. They drop it down the hole, all right? They hold it there, and then they bring another piece of steel casing up, thread it in, and then they keep throwing it down the hole. Okay, after that top hole is drilled, then a much bigger rig comes on the site, all right? And it re-enters the formation, that vertical hole, and it drills the horizontal, all right? And here's a big rig in Tioga County, Pennsylvania. And what will happen is this rig is going to drill 6 laterals on the site. Different top holes, all right? But each of the lateral ultimately extends a different direction into the Marcellus. Okay, and this is what it looks like on the platform. That's the navigator there. He gets logging information as he's drilling so he can sort of see where he is in the formation, and he steers the drill bit. And these guys, where are they? I've lost out here. That is actually one of those steerable drill bits. Okay, so now we have the hole drilled, got the horizontal drilled. Now a different group comes on the site, and they frack the well, all right? The first step is they lower, a perforation gun down into here, and they use plasma charges to blow holes out through the casing and into the rock, all right? Then they inject water, all right? Lots of water, about 4.5 million gallons per horizontal well on average, okay? And they inject this water down the well at very fast rates, and this increases the pressure in the formation until the pressure overcomes the tensile strength of the rock, and then the rock cracks and shatters. And they do this fracking in stages, so they might do a 100-meter long section at a time. All right? They're injecting water. In this area, a lot of the water comes from streams and rivers, but there's also chemicals in it, friction reducers, bactericides, some gels. And they always also, with that water, pump down lots of sand. I mean, a lot of sand, about 2 pounds of sand per 1 gallon of water. So they're pumping down thousands of tons of sand per single well. Why do they pump down sand? Well, if they stopped, once they lowered that water pressure and stopped injecting that water, if that sand weren't in there to prop up the fractures would collapse in on themselves again. All right, so the sand is called proppant, and it props open the fractures. So this is what a site looks like during hydraulic fracturing. It's an industrial operation. Here, can you see my pointer? There are 6 wells that are plumbed for hydraulic fracturing. This trailer here is sort of the command center. That's where they control the pump rates and the mixing of various chemicals. Around the site are a bunch of water tanks that hold water for fracking. These big conveyors convey sand to the blenders. Okay, and here's a close-up of those 6 wells that have been plumbed for the fracking stage. So after they frack, then the well is nearly ready to enter into production. Okay, you don't get natural gas by trucking it off the well site, but all of these natural gas wells are hooked up to a gathering pipeline. All right, and these gathering pipelines are subsurface pipelines, you can't see it here, all right, that travel to bigger transmission lines and bigger transmission lines and so forth. Okay, and so when the well enters the production stage, this is pretty much what you see. That is actually, there's just a single well on here. And then there's some equipment for some kind of primitive natural gas processing. This separates water, all right, from the natural gas stream, and these hold produced water that comes out of the gas well with the gas. So since 2004, when Range Resources drilled the Rents well in southwestern Pennsylvania, there have been over 10,000 wells, horizontal wells, drilled in the Marcellus Shale. Okay, and the Marcellus Shale sort of winds up from southwest to northeast, but you can sort of see some hot spots in here. One of them is in southwestern Pennsylvania, Fayette County, Washington County, and I can't read it now, Greene County. All right, and then come back. Up here in the northeast, Tioga County, Bradford County, and Susquehanna County, also pretty intense activity. So with this pickup in the intensity of drilling, we've also seen a pickup in the number of water quality complaints. This is work that was PADEP data that were analyzed by others. And since 2004, PADEP has documented about 4,000 water quality complaints in Pennsylvania. And this study also demonstrates a strong correlation between the number of wells drilled and the number of water quality complaints. So these water quality complaints, some are truly legitimate, some might stem from other factors. But it's instructive to look at, well, what are the processes, what are the mechanisms by which sort of this shale gas development might pollute people's drinking water? What has received a lot of more popular interest is actually contaminants migrating from the frac zone. They're injecting this water at great pressures, and so the idea is they're injecting these frac fluids, and these frac fluids under great pressure could migrate upward, all right, through into overlying drinking water aquifers. A lot of experts believe that, well, that's unlikely, all right? We have this basically mile-long intervening layer of, in this area at least, pretty fine-grained sedimentary rocks that should act as an effective barrier against that migration. But others have noted, well, there are ways that water could be short-circuited. One is through natural fractures that created through tectonic processes over geologic time. Maybe some of these are continuous, maybe not. What might be a greater concern are old abandoned gas wells, okay? We've heard a lot about drilling in Pennsylvania, the Marcellus Shale, but Pennsylvania has been drilled since the 1800s, particularly in the western part of the state. all right? And these old abandoned gas wells actually many of them penetrate the Marcellus, okay, and go on to deeper formations. So they could provide a conduit for the upward flow of fluids. The other mechanism, subsurface mechanism, has actually nothing to do with the process of hydraulic fracturing itself. Rather, it has to do with the integrity of the gas wells, how they're constructed and how they're cemented. All right? Wells that are poorly constructed can allow methane to migrate up the annulus between the casing and the side of the borehole. Okay? And this methane, because it's buoyant, it's a gas, may potentially go into drinking water aquifers. Now, the source of this methane could be deep down from the Marcellus, all right? But in Pennsylvania, above the Marcellus, there are a number of gas-charged geologic units. They might not even be economical, ever, all right? But natural gas is sort of ubiquitous in this section between the Marcellus and drinking water aquifers. Okay, so now I'd like to sort of return to the research questions. In a general sense, 2 research questions guided this study. One, we asked, well, how does groundwater quality vary across time and space in areas undergoing shale gas development? And once we were able to define that spatial and temporal variations, we were interested in what factors might be responsible for it. Okay, could it be shale gas development? Could it be other anthropogenic activities? Or could it be attributed to natural hydrologic or geochemical variability, or a combination of all of these? We've done a lot of different types of water quality analysis for a big suite of chemicals. Today's focus is going to be on methane, in part because methane has gotten a lot of attention by the public and regulators. I'll bring in other chemicals in as much as that they're needed to explain the methane data. So have a pretty unique study approach. Our first step before we did anything, and this took as long as the study has itself, was we developed a formal cooperative agreement between Yale University and a natural gas production company, Southwestern Energy. Okay? And the purpose of this agreement was that it gave us information on the locations of the gas well pads and the gas wells. It gave us the schedule for drilling and hydraulic fracturing of these gas wells. All right? It also led to, they gave us water samples from their fracking tanks and other information. So an important part of this agreement is that the university owns the data it collects, all right? And there are no restrictions on publication or any dissemination of the findings. The importance of this agreement is it allowed us to measure water quality responses, water quality changes in context of the various stages of shale gas development. And that's why this is I call it a prospective study, and it's what makes this study unique. So once we had this cooperative agreement hammered out, the next step was to select sites which we're going to install our monitoring wells for groundwater sampling. All right, and we did this relative to the location of planned gas wells. So we took drilling units that had yet been undeveloped, hadn't been drilled yet. We identified those. And then we installed 3 gas wells right next to the vertical section of the well pads on the hilltops, and 5 monitoring wells above the lateral section, but down in the valleys. One of the reasons that we focused on the valleys is because valleys are an area of groundwater confluence, so they collect groundwater from a bigger area. Okay, and so most of the land in Pennsylvania that is drilled and fracked is owned privately. Okay, and so to install our wells, we needed landowner consent, and this wasn't trivial. So we initially started off, we contacted 23 landowners. We did this with a mailing. The mailing described the purpose of the study. And it said that we might be in touch with them again to ask them if they were interested in signing a site access agreement, and which would allow us access to their land. So we contacted 23 landowners. We followed up with 14. 9 landowners that we followed up with agreed to sign the site access agreements, 5 deferred for various reasons. So the people who signed the site access agreements, we compensated them in the amount of $1,000 a piece for disruption of their property. So this is a map of our study area. The black lines here are shale gas laterals, okay? And these are planned shale gas laterals. Since we installed our wells, 7 of these have actually been drilled and hydraulically fractured. The red lines are the locations of our monitoring, or the red dots are the locations of our monitoring wells. Okay, the red dots with the black dot in the middle, all right, those are our monitoring wells that are right next to the well pad, all right. The other dots without, or the red circles without the black dots, are over the laterals. The yellow circles are our stream water monitoring locations. Okay, so this is our study area, but now looking south from the Susquehanna River. And I like this map because it shows how our monitoring sites are distributed across topography. Okay, you can see the hilltop sites near the gas well laterals, all right, and then the valley sites, or the hilltop sites next to the gas well pads, and then the valley sites. Okay, so having selected our site, the next step was to install our monitoring wells. And we installed our monitoring wells to depths of between 91 and 125 meters. Why did we pick this range? Because this is the depth that people's private residential drinking wells bottom at. And so we wanted to collect water that was representative of people's drinking water. The bedrock here is fine-grained siltstones and sandstones. Much of the flow occurs through permeable fractures. And we identified these fracture zones after we drilled the boreholes by a series of geophysical logs. All right. Then within each well, all right, we installed 1 to 4 sampling ports, 1 to 4 sampling intervals. The number of sampling intervals depend on how many fracture zones we encountered. All right. So these sampling intervals were isolated by packers. Okay, and each interval had its own dedicated pump to withdraw water from, and also pressure transducers. We're interested in groundwater fluid pressures because fluid pressures, more precisely the distribution of fluid pressures, drive groundwater flow and control groundwater flow direction. So sampling, we sampled these wells at a 14-day to 35-day intervals, typically once a month. And typically that was done with Erica and Jayoon. Always was done with Erica and Jayoon. Poor Martin didn't last very long. But then we brought those samples back to the lab, and we analyzed them for a suite of constituents, major cations and anions, trace metals, methane and ethane, isotopes of methane and ethane. They were going to tell us something about the origin of this gas. Then water isotopes, that tells us about sort of the origin of the water, and tritium, chlorofluorocarbons, SF6, and strontium. Gives us a little information about groundwater residence times. We also measured groundwater pressures, and we did this. This was done automatically in 1-hour intervals. And as I hinted at before, this was done at multiple depths per well. Okay, now get a little bit into the results. I'm going to focus first on groundwater quality in the near field, all right, close to the vertical section of the gas wells. And you'll see here that this is actually a Google Earth image taken at a good time because this site is being, right now it's actually being drilled. And our monitoring well is right on the edge of the well pad there. So we're close. Okay. And this was site F, and these are data, time series data on methane concentrations collected from a single port. Site F was our only monitoring well that had just 1 sampling port, just because there weren't many fractures anywhere else in the formation to conduct water. And on this graph, there's methane concentration on the y-axis, and these are dates. This is more than 2 years on the x-axis. You'll see that there are 3 vertical lines. The red line corresponds to when they drilled the top hole, all right, the vertical section of the well. The black line is re-entry. That's when they re-entered the hole to drill the horizontal. And the green line is when they fracked, okay? And you'll see that, concentrations, pretty low levels here. But then shortly after they frack, concentrations seem to go up. They increase by about a factor of 5. And so you look at this and you think, well, is the nearby gas well leaking? All right, is this a case of compromised well integrity? Well, one of the ways to sort of drill down to this is we can use information on the carbon isotopes of methane, all right? And the carbon isotopic ratio on this graph is described in terms of this parameter delta 13C. And basically, that's the ratio of carbon 13 to carbon 12, and then it's normalized by a standard, okay? More importantly than that, this graph is divided into 2 zones that are distinguished on the basis of the del 13. One, this green zone is the biogenic zone. This is biogenic methane, all right? Biogenic methane is created by microbes by reducing carbon dioxide or fermenting acetate or other very simple molecules. This is done under anaerobic conditions, okay? Biogenic methane has sort of a unique range. Generally in the literature, it's classified as relatively del 13 less than minus 64. So this is depleted in the heavier isotope. Okay, the other range is a thermogenic range, all right? Thermogenic gas is created by thermal degradation of bigger hydrocarbons, namely oil and kerogen. All right, it's called thermal cracking, okay? And this leads to an isotopic signature that's relatively enriched, about greater than minus 50. Marcellus gas is thermogenic, all right? It plots here, okay? So if you compare the timing of these 2 graphs, we see that sort of methane concentrations increase, all right, while the isotopic signature del 13C decreases, okay? And so what this suggests is that the production of methane in this case was done by microbes, all right, and is not associated with sort of a leaking gas well. It's not thermogenic gas. In fact, it's really highly depleted. Okay. So now I want to go on to another hilltop site. This is another site close to a well pad. All right. And this figure up here is actually taken from our monitoring well site. And what this is showing is they're flaring a gas well. And they sometimes flare these wells before they enter production, before they're hooked up to pipelines. Instead of starting off with methane data, I want to show you data on groundwater pressures, all right? And this well, site B, all right, has 2 sampling ports. Port 1 is actually the deeper port, all right? Port 2 is shallower. There's pressure here, all right? This is groundwater pressure, and then this is time. So if you look at the groundwater pressures in general, it's kind of smoothly varying. All right, not big changes in pressure. Groundwater flow this would suggest that groundwater flow is pretty steady, which is something you would expect of a bedrock aquifer. Okay, but these 2 spikes are pretty conspicuous here. Here and then here. This first spike is actually due to, it's a drilling-induced pressure pulse. When they drill through the top hole, they're using compressed air. All right, and so that compressed air shoots out into the aquifer and leads to this pressure surge. Now we think that this pressure surge might cause short-term effects in the turbidity groundwater. And we've also looked at its potential effects to sort of push methane that's near the surface out a little bit. But that's not what I want to talk about now. I want to address these less conspicuous little spikes here. All right. These spikes are important because what they do is they're sentinels, they're signals of a problem with the gas well. Okay? During our monitoring, this gas well developed a rupture in its production casing. I don't know if you can see it, but this is that rupture right here, okay? And they pulled this casing out during the remediation. That's how we know for sure that there was a rupture there, in part, all right? And this rupture, all right, produced that pressure blip, okay? To sort of understand the consequences of this, it might be useful to look at, once again, revisit sort of the construction of one of these gas wells, okay? This is the production casing here. Okay, this actually extends down into the Marcellus, all right? On the outside of this production casing, the annulus is filled with water, and then the intermediate casing, which extends down to 640 meters in depth, all right, is cemented to the surface, and then the surface casing surrounds that, it's cemented to the surface. So the rupture actually happened above the water table, okay? And so you think, well, that's not so bad then, but maybe. But what happens if that pressure was significant enough to drive the water out of between the annulus, between the production and intermediate casing, then methane could escape to the subsurface. And we actually know what the pressures were, and we know that those pressures were sufficient to eliminate that sort of water barrier. So the amount of methane that would actually leak into the subsurface, all right, would depend on the permeability of the rock at this location, the actual pressures, and how long the rupture went unfixed, all right, before it was patched or the well was plugged. Now, one thing to look at here is that this escape route is pretty deep. It's about 640 meters. Groundwater aquifer is up higher, several hundred meters. Okay, so these are another time series data of methane concentrations in 2 ports deep in a shallow port. And what I put on here is the timing of the rupture. And we know exactly when that occurred because that pressure wave propagated out, and it would do so really rapidly. Okay? And so you sort of see this little blip, all right, right after the rupture. Not much really, it sort of settles back down. But then several months later, methane concentrations, particularly in a deep well, climb, and then they drop back down. Smaller response in the more shallow port. So once again, we can sort of turn to our isotopic composition to look at sources. And if you look at our Del 13 data versus time, what we find is that after the rupture, methane concentrations in the groundwater samples were correlated with D13C of the methane samples. All right? In other words, as concentrations went up, the methane got more thermogenic. All right? Moreover, at least in these peak samples, we were able to detect ethane. Microbes, when they ferment or produce methane, they don't also produce ethane along with it. All right, but Marcellus gas, all right, is associated with ethane. So sort of this post-rupture correlation between D13C and the methane concentrations, all right, plus the intermittent detection of ethane suggests to us that that this rupture did lead to small, all right, additions of methane into the shallow groundwater reservoir. These concentrations, you know, some of you will see that and they'll say 0.1 milligrams per liter. That's really not much, okay? And it's not. Actually, it's more than 100 times less than if this were a drinking water well. It's 100 times less than what would trigger remedial action, all right? So it's pretty small. Okay, that theme, all right, in our other hilltops wells, even those that were uncompromised, plays out. These are data from our 3 hilltop wells, all right, and this data across the time series is summarized in terms of box plots, okay. So this is site B, there's 2 ports here, site F and site R. Has 4 ports there, all at different depths. The red line here is the median concentration. The box encloses the 75th and 25th percentile concentrations. So if you look here, the median concentrations never exceed 5/100 milligram per liter. All right? The variability in these concentrations are not that great, and generally concentrations are less than 2/100 of a milligram per liter. So they're quite low. We are, however, keeping an eye on Site F. In December, they're going to drill 2 new wells on that pad and frack them a couple of months later. So we'll be able to catch that. Now, if you look at methane concentration in our valley wells, the story is much different. Okay? Remember, the valley wells are positioned over shale gas laterals. Okay? And this is a similar box plot, and this is for 4 sites, Site A, D, H, L, and R. All right? All of these sites have multiple ports. All right? 1 is the deepest port in all cases, 4 would be the shallowest. Right? You'll see that at 3 of our sites, Site A, H, and L, median concentrations exceed 15 milligrams per liter. Okay? Even at Site R, concentrations are lower, but they're getting close to what the feds would say the level was be when remediation of that well is prudent. Okay? And so if you look a little closer, there are a couple of patterns. Methane concentrations tend to be greater at depth. Take, for example, Site A, where there's median concentrations are nearly 20 milligrams per liter, but at the deeper ports, there's nothing. So there's pretty substantial vertical variation, suggesting that this methane exists in sort of these thin veins. Okay, so now I'm going to focus a little bit on 2 of those sites that show significant methane. All right, one is Site A and one is Site H. All right, there are 4 lines on this graph. Okay. These are the 3 most shallow ports down here where we don't really see much methane at all. All right? But concentrations at the deepest port rise pretty precipitously at Site A and plateau around 23 milligrams per liter. Okay? Now you go to Site H, where we had 2 ports. Concentrations sort of show the same general feature, but concentrations in the deepest port max out around 70 milligrams per liter, and concentrations at the shallow port are around 40 milligrams per liter. You wouldn't want to carry a match near this water, okay? I always try to get Erica to go out there and get a picture of her lighting this, but she wouldn't do it. But this would ignite, okay? And you say, well, I've put these lines on here that indicate the time of top hole drilling, re-entry, and fracking. And you'll say, well, okay, concentrations where they increase started before this, all right, but they really sort of spring up afterwards, okay? And so you would say, well, that sort of overlap, the relationship of that timing is at least suggestive of a shale gas development effect on the water quality within these wells. Okay, so to sort of tease this out, we turned back and we began to look again at the isotopic composition of the methane and also the hydrocarbon composition in the groundwater samples. And this is for Site A, all right, the deep port, and the plot at the top is called Bernard plot. It's a plot of the ratio of methane concentration in the groundwater to ethane, okay? And basically, on the x-axis is the del 13C of methane. And there are 2 zones here. One's the biogenic zone, all right? The biogenic zone is characterized by methane to ethane ratios that are greater than 1,000, all right? Microbes don't create, as I said before, much ethane during methanogenesis, all right? And on the x-axis, it goes down to about minus 64, so this biogenic gas is relatively depleted in the heavy isotope of carbon. And then we have the thermogenic range, all right? It's more enriched in the heavier isotope, minus 50 and greater, and it has methane to ethane ratios typically less than 100. And so you can see that the Marcellus Shale, all right, and these are samples that we collected from the gas well, plots pretty well in the thermogenic range. These samples are groundwater samples from A1, all right, and they're consistently in the biogenic range, all right. We can also look at these data a little differently, all right. Instead of methane to ethane on the y-axis, we can plot the hydrogen isotope ratios for methane against the carbon isotope ratios of methane. And this plot has 4 zones. One's a biogenic zone, one's wet thermogenic, one's dry thermogenic. Dry thermogenic is more thermally mature gas than wet thermogenic gas. And then the mixed zone, okay? And that's what happens when you get waters that from different sources where you have mixtures of thermogenic and biogenic gases. But once again, at least at Site A, these gases tend to plot in the biogenic zone. So this once again suggests that, well, this is methane production was independent of shale gas development here. Now, at Hinkle, where we saw the unusually high concentrations, the story is not so simple, okay? This is the Bernard plot across the top. There's green and red symbols there. Those are data collected from our 2 ports at Hinkle, one shallow, one deep, okay? And these data seem to plot in no man's land, all right? And what this suggests is this isn't anything that's that remarkable. It just suggests that the gas here is a mixture of thermogenic and biogenic gases. Now, if we go down here, all right, we sort of seen the same thing, all right? And we see that things are plotting as a mixture. But what's interesting here is that this represents a time trend too. And so in these groundwater samples, the del 13C is getting larger, all right? So what that means that over time, all right, this methane in these groundwater samples is getting more Marcellus-like, okay? So the obvious question is, well, is Marcellus gas mixing into our groundwater? And one of the ways that we can address that is with a mixing model, okay? And this mixing model has 2 components. One is methane to ethane, all right? And the other is the carbon isotope ratio of methane. One end member of this mixing model is Marcellus gas, all right? It's very enriched. It has a del 13C of about -32, all right? It's a wet gas, has a fair amount of ethane, well, compared to biogenic gas, of about -50. The other end member of this mixing model we used was based on the composition of the water that we collected from Hinkle before they did drilling, all right? And so these are sort of our baseline, our pre-drill estimates. And these pre-drill estimates have a high methane to ethane ratio in port you can see it. I can't do it right now for some reason. In port 1 and port 2, okay? And they're relatively depleted in del 13C. So if Marcellus gas were entering our groundwater samples, then we'd expect our post-drill samples to fall somewhere along this line. And they clearly don't. We greatly underestimate with this mixing model methane to ethane ratios. So this is pretty convincing evidence that this isn't Marcellus gas, all right? All right, this gas came from somewhere else. And so this suggests that, well, we can't attribute this rise in methane concentrations to a loss of well integrity that would leak methane into the aquifer, or even from moving of methane up from the frac zone during hydraulic fracturing. So if it's not Marcellus gas, what is the source? We needed an alternative explanation, all right? One of the things that we found was that, these are Site H data, is that our concentrations of methane were positively correlated with salinity, okay? Salinity reflects the collective composition of ionic species in solution, inorganic ions. And so here are graphs of methane versus lithium concentrations, methane versus strontium, methane versus bromide, and methane versus barium, okay? These are all components of salinity. And in each case, a good amount of the variation in the methane data can be described by increases in the concentration of these ions, okay? And we could try this for other ions, and we have, like chloride, sodium. We all see these same relatively tight correlations. Moreover, we can say, well, I don't want to look at just site H. I want to look at the valley wells, site A. And we also see this correlation between salinity, all right, and methane concentrations. So the significance of this is this covariation suggests that the source of methane and the source of salinity are the same. Okay, so if we can figure out what the source of that extra salinity is, that increasing salinity, then we can reasonably infer what the source of the methane is. Okay, and one way that salinity sources in groundwater are identified is through consideration of elemental ratios. Okay, and this is a graph of chloride concentration. The ratio of chloride to bromide concentration is a function of chloride concentration. And these data are from all our sampling sites plotted on here. Okay, different colors, different sampling sites. Okay, superimposed on these observations are two mixing lines, end-member mixing lines. All right, these describe how the chloride to bromide ratio would evolve as the sources as two different water sources are mixed in varying proportions. Okay, so for example, this line up here, all right, this would describe how our most shallow groundwater, this chloride to bromide ratio in our most shallow groundwater would evolve if it were mixed with increasing volumes of groundwater that was impacted by road salt runoff. Okay, road salt halite, or largely. Okay, that's one mixing model. All right, our data don't follow that very well. But we have this other mixing model here. And this mixing model is created by mixing that same shallow groundwater, all right, with varying amounts of water derived from deep formations, all right, that underlie the freshwater aquifers at our sites. And this is sometimes called Appalachian Basin brine. And if you look at these data, the data from our Hinkle site, the green data points, fall pretty nicely on this line, all right? And actually, if you drill down into this more, the data from all the valley sites, all right, fall along this Appalachian Basin brine mixing line, all right? This result suggests that the groundwater chemistry at site H, as well as at our other valley sites, is being affected by small inputs of deep groundwater, deep salty groundwater. So this sort of leads to the notion that the methane increases at Hinkle are derived from a transitional zone, okay, that from Hinkle and the valley sites that lies in the subsurface horizons above the Marcellus Shale, but below the fresh groundwater aquifer. Okay, this schematic is intended to illustrate that. And so I've sort of divided it into three sections. One is deep basin, all right? Deep basin is low, it's below fresh groundwater zone, it has high salinity. This is connate water. That's probably water that's been trapped in there since the rock formed. It's actually more saline than seawater because that seawater is evaporated as the rock formed. It's thermogenic, okay? It's definitely methane laden, and that it's thermogenic in origin. All right, where'd that methane come from? It might have come from that rock itself, all right? Or it could have been delivered up from deeper formations very slowly over geologic time. Natural gases migrate, all right? This deep basin has low permeability, all right? Flow's stagnant, all right? There might be some flow, but not very much. Above this is the transitional zone, all right? It has moderate salinity, okay? Probably wouldn't want to drink this water, you'd taste the salt. But it has it's also charged with methane of mixed thermogenic and biogenic origin. Okay? And then the shallow groundwater zone, this is the zone of where flow is most dynamic. All right? It's largely meteoric water that's been recharged recently. All right? But it gets its methane, all right, from, and high salinity, largely but not exclusively from the underlying transition zone. So what this suggests, according to this model then, is that the increases in methane in our valley sites, not just Hinkle, but our other valley sites, results from increasing methane fluxes from deeper zones, the transitional zone. All right, and this flux could reflect either an increase in upward groundwater flow, all right, or an increase in the concentration of methane in the transitional zone that feeds the shallow aquifer. Our hydrologic observations at this site indicate that groundwater flow is fairly steady, all right? It's not changing a lot with time, all right? Typical of a bedrock aquifer. So what this suggests is that this transitional zone is not, but it doesn't behave like a well-mixed reservoir, all right, but is heterogeneous with respect to its methane concentration and isotopic composition, all right. So we think this conceptual model is sort of, I've indicated here, it's inspired by others, but our time series data helps tease this out. So I'm running out of time. Wow. Okay, so in conclusion, one of the things that we found at this site, which hasn't been elucidated before, is that there's a strong depth dependence on methane concentrations. Right? That has implications to you if you're a homeowner. As a homeowner, you might think if I install a deeper groundwater well, I'm protecting myself from surface sources of contamination. But in this region, at least, there's also a good chance that you're increasing the likelihood that your well will be impacted by methane. Elevated levels of methane in groundwater beneath valleys are the rule, not the exception. We've seen that here. This is beginning to emerge from other studies. Okay? So one of the things that this suggests is the potential that topography might be a better predictor of methane occurrence than proximity to natural gas wells. All right? Groundwater methane concentrations exhibit considerable temporal variability. This makes things challenging. Often what happens is, according to regulations, to protect homeowners against potential contamination from shale gas wells, is they'll take a measurement of their water quality before fracking and one after. And they'll compare these. If they don't change, everything's fine, but if they do change, then there's an issue. All right, but this temporal variability, this natural variability, can confuse those assessments. And then finally, in our study area, shale gas extraction has had detectable effects on groundwater flow and quality. I would categorize these as not adverse. But this doesn't necessarily exonerate the shale gas industry. I'm not suggesting that our study shows that shale gas development is safe if you're worried about your water quality. It's a small study, all right? There's no study like it so far, but this study needs to be replicated, all right, if we're going to do a better job at understanding the vulnerabilities. And before I stop, I want to acknowledge my funding sources. We actually did this on a shoestring budget. We got money from Southwestern Energy to install the groundwater wells, money from JP Morgan Chase, the National Science Foundation, which paid for part of my summer salary, the Yale Climate and Energy Institute, and the Yale Center of Business Environment. And finally, acknowledgments for people that contributed to the study in various ways. Thank you.
Well, unfortunately, we are out of time. I know there are folks who want to ask questions. We know where to find them. So please join me in thanking Jim Saiers.
Thanks. Time got away from me. Well, it doesn't end the way many of us hope.
Yeah, no. Well, but it's a small sample. So
Yes,
we don't know
yeah.
which, yeah, but no, that was really interesting.
Good, thank you.
Thank